Earth is changing. The very few forces that have shaped our planet for millions of years are not being transformed by us. Welcome to episode 16, The Climate Code, the science of a changing planet. From the moment we first looked up at the skies and wondered how the weather worked, humans have tried to understand how these forces drive our planet's climate. Ancient civilizations tracked these stars, they observed seasonal patterns, and they relied on the rhythms of nature to guide their lives. But in the past century, a major shift has occurred, a shift from curiosity to action, as the science and technology begin to reveal an uncomfortable truth. The climate is changing, and we are the cause. The evidence is no longer scattered observations or isolated events. It is a global pattern, consistent and undeniable. Let's take a dive and look at science and climate. We know that climate models are at the heart of modern climate science. They take in what was once a widely debated theory that human activity is significantly contributing to global warming, and they turn that into something we now recognize as a fact supported by overwhelming evidence. These models are incredibly sophisticated. They were built over decades and they incorporate massive amounts of data from diverse sources like satellites, ice cores, ocean buoys, and weather stations across the globe. They stimulate complex interactions between the atmosphere, ocean, land, and ice, which allows scientists to test different scenarios and see how the Earth's climate responds. What's truly compelling is that these models don't just project the future. They're also accurately reproducing past climate event patterns, including warming trends that we've already observed. And when natural factors alone, like volcanic activity, solar cycles, are plugged into these models, then they can't really explain the rapid warming that we've seen in the recent decades. Only when human emission is plugged into these simulations, they aligned with the actual temperature rise. In short, the evidence is unmistakable. Human activity, particularly the burning of fossil fuels, is a primary driver of current global warming. Climate models have not only confirmed this, but they become an essential tool in helping us to prepare for what really lies ahead. Take the Killing Curve for instance. The graph shows the rise in carbon dioxide levels in our atmosphere for the past 6 decades. Since the Industrial Revolution, it's been climbing at an accelerating rate. What's the cost? We've been burning so much fossil fuel, oil, coal, and gas, which have been releasing so much carbon that has already been locked away in the earth for millions of years. Each time we drive a car, we fly in a plane, or we power a factory using these fuels when pumping more CO2 into the atmosphere. The Killing Curve provides clear, measurable evidence of this trend with seasonal fluctuations layered over an unmistakable upward trajectory. It's not just a line on a graph, it is a record of human impact, a warning sign from our planet. And if we don't act to reduce emission, that line will keep rising along with global temperatures, sea level, and extreme weather events. Climate models predict the future, and when human emissions are included in these models, the temperature rise we're seeing is exactly what these models forecasted. It is not just a model that confirms it, it is the real-world evidence that matches them. These models take into account greenhouse gas concentration, solar activity, volcanic eruption, and other natural factors. We've seen rising global temperatures, shrinking ice sheets, more frequent and intense heat waves, and shifting weather patterns, which all have been predicted by these models decades ago. The accuracy of these projections strengthen our understanding that human influence is the dominant force behind the climate change. They're not just theoretical tools, they're windows into our future, and they're showing us what's at stake if we continue on this path. Let's dive into math and climate now. So, mathematics plays a pivotal role in understanding and predicting the climate. Climate models are rooted in complex mathematical equations that stimulate everything from ocean currents to atmospheric circulation to even radiation. These models use the law of physics, like thermodynamics and fluid dynamics, to calculate how heat moves around our planets. They do this by breaking the Earth's surface and atmosphere into a 3D grid. Scientists use equations to compute changes in temperature, pressure, humidity, and wind at each point over time. It is an enormous computational task that requires supercomputers to solve, but it is through these mathematical frameworks that we can forecast future climate conditions, as well as estimate sea levels rise and predict extreme weather patterns, as well as understand the long-term effects of greenhouse gas emissions. And without math, we wouldn't just lose precision, but we would also lose our ability to see the trajectory we're on and the potential consequence of inaction. There was a time when predicting the weather beyond just a couple days felt more like guesswork rather than a science and more like an art. But today, thanks to the enormous advances in computational simulations, our ability to forecast has improved dramatically. We can now not only predict short-term weather with much more greater accuracy, but we can also be able to use these models' long-term climate patterns and trends with increasing confidence. This is made possible by powerful supercomputers that process trillions of calculations every second. The machines simulate Earth's atmosphere, ocean, and land systems in high detail, allowing scientists to explore a wide range of possible futures. They run multiple scenarios, adjusting variables like carbon dioxide levels, deforestation rates, and ocean temperatures to see how different choices and natural events could impact the climate over time. These simulations help understand everything from how greenhouse gas influence global temperatures and how extreme weather events like hurricanes, drought, and heat waves might shift in frequency of intensity. In essence, we're no longer flying blind. Computational modeling gives us a much clearer window into both the near future and the long-term trajectory of our planet's climate. This process builds on the early work of Svante Arrhenius, a Swedish scientist who in 1896 was one of the first to suggest that increasing levels of carbon dioxide in the atmosphere could warm the Earth. Though he worked with modern tools, his calculations laid the foundation for understanding the link between human activity and global temperature. Today's powerful climate models are a continuation of that legacy, turning a once theoretical idea into a vivid picture of what's ahead if we don't take action. So we know that computational models allow us to simulate different scenarios. What happens if emissions continue at this rate? What if we never take action to reduce them? These models help us answer those questions, and they also help us prepare way better. Now let's talk about the solutions. The good news, we're not powerless. In fact, technology is leading the charge in the fight against climate change. Solar and wind energy are the backbone of a cleaner, more sustainable future. These resources tap directly into the power of nature, sunlight, and wind without producing the harmful emission that fossil fuels release into the atmosphere. Over the past decades, we've seen incredible strides in making these technologies not only efficient, but more affordable and widely available. From rooftop panels on homes to vast wind farms stretching across our plains, green energy is no longer out of reach. It is becoming the norm. But it's not just that we can generate clean energy. It's how we store it and deliver it when it is most needed. That's what advanced battery storage technology comes in. These systems allows us to capture energy when the sun is shining or when the wind is blowing, and then it releases it later, like in the evening or during periods of high demand. The ability to store renewable energy effectively bridges the gap between supply and demand, solving one of the biggest challenges in transitioning to a fully renewable grid. It is key to make renewable energy not just clean, but consistent, dependable, and scalable. And the best part, this isn't theoretical anymore. It is not a distant dream. These technologies are real, they're operational, and they're already reshaping the way we power our homes, our cars, and our entire communities. The clean energy revolution isn't coming, it is here already. Now let's take a turn into education. One of the most important shifts in recent decades is how climate science has become a central part of what students learn in the classroom. What was once reserved for experts and researchers is now accessible for students all around the world. Climate science has moved from the edge of academia into the heart of the classroom. Teachers aren't just lecturing, they're facilitating discovery. Students today aren't just memorizing facts about the environment, they're experimenting. They're coding simulations as well as building renewable energy models. And they're also interpreting real-world climate data. They're doing what great thinkers have always done, asking questions and seeking answers. Even in ancient times, philosophers like Aristotle studied the natural world with curiosity and rigor. He believed that understanding nature was a key to understanding ourselves. That same spirit lives on today in classrooms when students investigate the atmosphere or explore ecosystems, or even when they measure the human impact on Earth's climate. That kind of learning is transforming. By integrating climate science into classrooms, we're doing more than just teaching a science. We're empowering a generation that not only is informed but equipped to innovate, lead, and take action. They understand the changes ahead, and more importantly, they believe that they can be a part of the solution. Climate change isn't just an environmental issue. It's reshaping global policies, economies, and human survival strategies. From the Paris Agreement Act to carbon pricing, governments are now acknowledging the urgent need for action. The impact of climate change is felt in every corner of the globe, from the rising sea levels to threatening coastal cities to the droughts and wildfires that devastate landscapes. The consequences are clear, and we've learned that the cost of inaction is far more greater than the cost of change. But alongside these challenges comes an opportunity. The shift towards renewable energy, climate-resilient infrastructure, and as well as sustainable practices in creating new jobs, new markets, as well as new possibilities. The global economy is changing, and with it, the way we live and work as well. The climate code isn't just a problem to solve. It is a story that we're all writing together, and while the changes are enormous, the progress is undeniable. Science, mathematics, technology, and education are our tools. They're helping us navigate the climate crisis and forge a path toward a more sustainable future. The code is cracked, the solutions are within reach, the future is in our hands, and together we can change the course of history.